All right, guys. So what we're doing today is factoring. We are doing special factors. We're going over special types of factors today. Now, one of the types that we're not going to look at comes in the form of a squared plus 2ab plus b squared. And if we have this here, it's really going to look like a plus b times a plus b. So it's going to be the same thing in both sets of parentheses. So an example of this here would be saying x squared plus 4x plus 4. This one here would be an example of this special type of factor. What we would call this is a perfect cube trinomial, or perfect square trinomial. Because what this works out to be is x plus 2 times x plus 2, which we can really write as x plus 2 squared, or this here is the same as a plus b squared. So it's just the same thing times itself. It's a perfect square trinomial. Now we also have this in subtraction because it could be a squared minus 2ab plus b squared. And the only difference between this one and the first one is just saying that it would be a minus b squared. It would be a minus b times a minus b. Now we don't specifically cover this or delve into this because the method or the shortcut, quote unquote shortcut to solve these and factor these isn't really any faster than what we did last week with factoring. Doing two sets of parentheses, finding the sign, factors of the first and third term would work just fine with any of these here. So there's not a big reason to go over the shortcut method than if we were just going to factor it already. Now the one that we are going to cover is the difference of two squares, or the difference of perfect squares. This one here, the shortcut is a little bit faster and a little bit easier to work with. So the difference of two squares, well, we have a squared minus b squared. If a and b are both perfect squares, I can rewrite it as a number times itself. For both of them and they're being subtracted, it would be a difference of perfect squares, such that a squared minus b squared is equal to a plus b times a minus b. Well, if we look at an example of it, x squared minus 9 would be a difference of perfect squares. X squared would be x times x times itself. 9 is a perfect square. It would be 3 times 3. So we could set it up as x squared minus 3 squared. And it ends up factoring as x plus 3 times x minus 3. So if we notice the first and third term, the two terms in both parentheses are the exact same. We have x and 3. The sign in the middle changes. And that's it. Now, if we look at the first one here, x squared minus 25, is this here a difference of perfect squares? Can I rewrite x squared as a number times itself? It'd be x times x. What times itself is 25? 5 and 5. So is this a difference of perfect squares? Well, yeah. So we'd have our two sets of parentheses. One of them would be positive, the other would be negative. For x squared, we would have x and x. For 25, we would have 5 and 5. And that's it. That's all we have to do for this here. Any questions on this here so far? Now, if we wanted to check it, we can. X times negative 5 would be negative 5x. 5 times x would be plus 5x. And negative 5x plus 5x is? Negative 5 plus 5, or 5 minus 5 is 0. Is that the correct middle term? Well, yeah, we don't have a middle term, do we? So it would be 0. So this is the factorization for this here. Questions on this here? We're ready for the next one. 4z squared minus 1. Is 4z squared and 1 perfect squares? Can we rewrite it as a number times itself? Well, 4z squared, well, z squared would be z times z times itself. 4 is what? 2 and 2, yeah? So we could rewrite 4z squared. Well, that'd be 2z times 2z. How about 1? 1 and 1. So this here would be a difference of perfect squares, yes? So in our two parentheses, we would have opposite signs. And in the first one, we would have 2z plus 1, and then we would have 2z minus 1. And that's it. Questions on this here? You like these so far? X squared minus 64. Would we consider this a difference of perfect squares? Because this x squared would be what? X times x. 64 would be? Okay, so what would our factors be? So x 8 times x. I mean, we could have done it in either order. We could have said x minus 8 times x plus 8. That'd be the same thing. As long as one's positive and one's negative, that's it. Questions on this here? X squared minus 36. Is this a difference of perfect squares? 36 would be what? 6 and 6. X is still just x and x, so this would be x plus 6 times, yeah, we could have had it as x minus 6 times x plus 6. That's it. Now this one here is very helpful to know because, I mean, we could still do the same method, 3 sets of parentheses, 3 sets of parentheses. Now, since we don't technically have a middle term, we can consider it to be 0x. So the third term would be our 36. So we did the 2 sets of parentheses to find the sign. Well, the third term here would be negative, so our signs are opposite. Positive, negative. Factors of x squared would be x and x, and then we could try 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't work, and then 6 and 6, and try each one of those to see if it works to do the other method. But both of these are being subtracted, and they're both perfect squares, so it means it has to be this here. So this method over the other one, this one is faster, because if we notice that they are perfect squares and they're being subtracted, this is how they're going to factor every single time. So this is faster. And luckily, once you all start seeing the pattern of how this works, it makes it very easy. This is normally one of the favorite ones to factor out of any of them. How about this one here? Is 100 a perfect square? Is m squared a perfect square? Okay, so we can do this. We would have opposite signs, and what would be our 10 and then m, 10 and then m. Because the m came second, because it's minus m squared, the m has to go second. And it's not so much for the first one, the 10 plus m, because we can flip those. We can add two things in any order. But the second one, the 10 minus m, if we flip it, we get the wrong thing. Yes, because if we had m plus 10 times m minus 10, and I'll go on and multiply this back out, because if we distribute and multiply through, m times m would give us m squared. M times negative 10 would be negative 10m. 10 times m would be plus 10m. And 10 times negative 10 would be negative 100. These would cancel out, telling us that this is m squared minus 100. Well, what did we start out with? 100 minus m squared, yes? Is 100 minus m squared the same as m squared minus 100? No, they're going to be two separate things. Now, could we have gotten it so that m was in front? Well, yes. But to rewrite that, we would have negative m plus 10 times m plus 10. I'd have to have that m negative. Now, we could factor it out and say negative, parentheses, m minus 10 times m plus 10 to factor that negative out to get it to look like this. But that right there is fine. We don't have to have m first. It's nice to have it first, but it's not always necessary. We can have it second. Questions on this here? How about this one? 9n squared minus 16. 9n squared minus 16. Is 9n squared a perfect square? Because what times itself is 9? 3 times 3 is 9, n times n would be n squared. 16 would be 4 and 4, 4 times 4 is 16. So this here would be, well, 3n minus 4 times 3n plus 4. And if seeing some of the numbers to see if they are perfect squares is kind of challenging. I mean, variables is fine because if it's squared, we can say it's multiplied by itself, yes? But with the numbers, I can always grab the yellow or graphing calculator and take the square root of 9. Does it give me a whole number? If yes, so that number times itself would be our number. So if you got, say, 169, is 169 a perfect square? It is. It would be 13 and 13. Three and 3 is 9. 3 times 1 is 3. 0 gives us 169. 169 is a perfect square. But if we don't know that off the top of our head, we can take the square root of 169, hit enter. It tells us it's 13. Okay, so that means 13 times 13 is 169. So the calculator will help us with perfect squares to make sure we got the right ones. But do we feel pretty comfortable with this here? Okay, I want to add one in. Let's see here. I know I did 81 minus make sure. No, it's not one. No, that's not it. Because 5 here, the 4. There it is. Yeah, I was trying to make sure I got this the way I wanted it. Now, 81 and 225. For those of you, I don't know if any of y'all actually have a calculator on you. Are they perfect squares? Is there a number that times itself is 81? 9. Is there a number that multiplied by itself is 225? It is. There's 15. Is there a greatest common factor between 81 and 225? Well, 81 is 9 times 9, yes? Let's see here. Well, 9 will go into 22 2 times, 18. And that would be 9 divided by 45 is 5. Oh, we'd have 25, yes? Wait a minute. Is 25 a perfect square? So let's just say I factored out the 9. 81 divided by 9 is 9x squared. And as we see here, this is 25y squared, yes? Is it still a difference of perfect squares? Yes. So there are some where we could actually factor out a greatest common factor and end up with perfect squares. Because 9x squared and 25y squared are perfect squares. Which we can do the same thing and say 9 times. Well, what times itself is 9? We have 3x and 3x. What would 25y squared be? 5y and 5y. Now, if we'd have left the 9 factored in, really we're just multiplying both of these by 3. It would have been 9x plus 15y times 9x minus 15y. I mean, both of these are the same set of factors, but the big issue is I'm not going to make a big stickler about this on the homework assignment. There is one like this on the assignment because it just says factor. Now, the place that you will find that you will get this wrong is depending on the rules, or not the rules, but the instructions. Because if it says to factor the following polynomials completely, the one in green is not complete. Because greatest common factor is a part of factoring, pulling it out. So 9 and 15 both have a greatest common factor of 3. So if it's not pulled out, it is not considered to be factored completely, all the way down. It would take the one in blue, it's the one it wants. Does that make sense? So really the only main difference is completely. If it asks to factor, both of these are technically factored. Blue is factored completely, green is not. And that's the only main difference. Will it make a difference in when we solve it? Well, no. Because again, we would set both of these equal to 0 and solve, and the factor would come back out. Any questions on this here? All right. We good with special factors, the difference of perfect squares, or difference of 2 squares? You all think it was very creative how they named this? I mean, difference is what? Subtraction? And what are we subtracting? 2 squares. So it's the difference of perfect squares. They pretty much just named it exactly what it is. If I haven't pointed this out to y'all before, but if you notice most of the things that we describe in math and the titles that are given are exactly what they are, there's not anything real clever to it. They name it 100% what it is. Yeah, they weren't, some of the mathematicians who came up with it weren't too creative, so kind of easier to memorize it, but other than that, this is the last thing we'll cover today. It's 54 squared minus 48 squared. Now we want to use the special product pattern. So what we were doing, so what we'd be saying is, well, we could rewrite this as 54 plus 48 times 54 minus 48. Well, we can add these two together, which would be 102. And 54 minus 48 is 6. And at this point here, we can multiply these together. 6 times 2 would be 2. Carry the 1, which would be 0, 1. So we get 612. This is very effective if we don't have what? what would be a more effective way to take or solve 54 squared minus 48 squared? Exactly. I mean, will a calculator solve out 54 squared minus 48 squared? Would we have to do anything? No. I mean, we could literally type 54 squared minus 48 squared into a calculator and get the answer. But if we weren't able to use a calculator or didn't have one, this is actually a very easy way to actually figure out what the difference of these two numbers is. Because 54 plus 48, we can add those. That's not bad. 54 minus 48, we can get that as 6. 6 times 102. We can do that on paper. That's not as bad as trying to take 54 squared minus 48 squared. That would be a massive number to try to calculate out. This here is a little bit more effective. And then again, this here, I mean, we could just type that in and hit enter and be done. Because if we did this by hand, it would be 68 plus 62 times 68 minus 62. Well, 68 plus 62 would 0 carry the 1, which would be 130. 68 minus 62 is 6. And 130 times 6 would be 780. Any questions on this here? And that's it. We are not doing anything else in 3.2. The only other part of 3.2 is our perfect square trinomials, which they're the same thing as what we did last week. So we're not going to worry about those. But that is it for 3.2.